Hello, welcome back. We were discussing the problem that we had, just a practice problem on the shock wave. And what I've done is I've just basically done a representation of that figure that we were drawing in my Google Doc. So if you go here, okay, trying to see if I can save and close. Okay, I'm trying to see if I can save this. Let's see. So I'm trying to solve that practice problem you were working on. And here's that document. Okay, so what I'm trying to do is I'm trying to represent the problem. So this is the location. Everybody still sees the drawing, right? X equal to 10. The flow rate is, and flow rate and density is listed here. Everybody's seeing that, and I got this. And based on that, we derived the speed of this shock wave, which was 17.65. So I can actually write down the slope of this line. So this line will have a slope of negative 17.65 over 60. And one point on the line is time equal to 6, x equal to 10. Okay, tell me if that makes sense to you. So for this line right here, I have the slope, which is negative 17.65 over 60 and 610. And then for this line, which is basically going to be relieving congestion, because at t equal to 20, the flow reduces. And then reduced flow will be moving at 100 kilometers an hour. So basically the same parallel line as this one. But, and then the line slope will be 100 over 60. And then the one point on this particular line will be 20 and 0. Okay. So questions. So is that an accurate representation of what we had covered earlier? All I've done is I've added the slope. I've drawn a figure in which I've added the slope of the lines for which I want to find the intersection for. So can you now do me a favor and try to find where this shock wave that was forming meets with this free-flowing travel demand, which is a reduced flow rate? When do these two lines intersect? So let's take a few minutes to try to figure out the point that I'm about to highlight here. What is the coordinate of this point right here? It's the intersection of one line which has this slope and one point on this line, and then this line which has this slope, and then this is one of the points on the line. So what you'll need to do is you have to find the equation of each of these lines in x and t and solve those. So let's go ahead and take 5 minutes to do it. Okay, so we are here to practice now. So we're going to take the next few minutes to try to practice that out. If there are any questions, if you cannot figure it out, please let me know, and we can go over this. But what I want you to do is, because remember, we are trying to find, this is the extent of the shock wave. This is how far back the Q goes. And for that, we need to find out where does this first originally forming shock wave meets up with this reduced demand. So we figured out the slope and one point on the line, slope and one point on the line. We figured out equation based on that, and we just figured out the intersecting point then. Okay, so let's do that. Let's do some practice of that and see what happens. If you have any questions, please let me know. I'm gonna be pausing the recording for a minute. Okay, so the coordinate of this point then are, close and come back to it. So the coordinate of this point then are 23 and 5. Okay, so what does that tell me? That means that the shock wave is going to move back it starts at t equal to 6. It's going to move back for about 17 minutes. And it will get to the point where x equal to 5. Remember, your ramp is at x equal to 3. So it's not actually going to go back to the ramp, which is fine. But the idea is that 23 and 5. Okay, so 23 and 5 is good because it takes 3 minutes, which is also good, right? 5 kilometers. And once you figure out the x coordinate is going to be 5, you know that t equal to 20 means it will take 3 more minutes to get there. Okay, so now can you figure out the max Q? Max Q now is very simple to figure out because this is 5 kilometers. And then you know the density is 72. So then you can figure out that, hey, my max Q will be 5. It goes 5 kilometers back, and I have a density of 72 in that. So my Q silent will be 360 vehicles. I will have 360 vehicles lined up in the queue, or at least be affected by Q, according to the shockwave method. Okay. Now, only thing I need to figure out now that I haven't yet figured out using the shockwave method is the speed of this shockwave. And the speed of this shockwave, I have. So first of all, we have to figure out what 2 regimes is this shockwave separating. Yeah, what 2 regimes is this shockwave separating? Now, this is your traffic regime right here. So I know one of these traffic regime is this one, 3200 and density equal to 72, which is my congested one. For the uncongested, I know it's very easy to figure out flow and densities, but I just don't know what the flow rate is yet. Maybe we know, maybe we do. Let's figure out, go back to the problem and see if we can figure out what is the flow density on this sort of free flow traffic regime. Do we have that information? 2600, I hear 2600. Let's take a look at where Dana is getting 2600. So I'm going to go back to my problem and I'm going to clear all the drawings. So if I go back to the problem, what happens at t equal to 20, the demand reduces to 2400. So should I use 2400 vehicles per hour as my flow rate? No, right? I can't use it because there is 200 vehicles per hour from the ramp. Okay, there is 200 vehicles per hour on the ramp. And that means that I have something else going on. I will have total flow rate of 2600 that's going to be coming in. Okay, so if I go back to this original figure that I was drawing, if I want to get the text here, so if I want to put a text box here, what is my Q value? It's actually going to be 2600. Is everybody clear on why it's 2600? And then once I know what the flow rate is, I can also figure out the densities, right? In the same way, I can figure out K also. It's actually just going to be 26 also. Because it's uncongested regime, I have a simpler equation. I figured out the Q equal to K as well. Okay. So I figured out the Q equal to K times 100. So even though that relationship is per lane because it's proportional and 2 lane and there is no plus or minus going on in that equation, it's a fairly simple equation. regardless of whether I divide by 2 and then multiply by 2, I get the same number. So I know quickly that the density is going to be 26 here. Is everybody clear on this? Okay, now what I want you to do is I want you to get me the shock wave speed for this one. You know the flows and density. I need to know the speed of this shock wave. Okay, so let's take another couple of minutes to figure out the speed of this shock wave. And remember, to figure out the shock wave, I just need to know what is the flows and density of the two regimes that my shock wave is separating. And that's all I need. So that should be okay to do. Okay, I see some responses in the chat already. So the answer that I'm seeing is 13.04, which seems correct to me because I'm dividing 600 is the difference. 600 is the difference. And I'm dividing that by 72 minus 26, which is 46. Yeah, 13.04. What's the sign of this? So I see a couple of people responding with the same answer. That's good. But what's the size? What's the sign of this shock wave speed? Positive, right? Did you all get positive? Right? Yeah, it's positive. That means it moves with traffic. You can see this has a positive slope. So now we also know that this speed has a shock wave speed of, so I'm going to write down the speed of the shock wave or slope of this line is 13.04. And 1 point on this line. Do we know 1 point on this line yet? Do we know either of those points? Do we know this point or that point? Actually, we know this point. So 23.5, we already figured that out. That's good. Do we know this point? Do we know the coordinate of this point that I'm highlighting on the screen right now? Do we know yet what the coordinate of the point being highlighted on the screen are going to be? What is the coordinate here? We know the x coordinate is 10. I mean, we know the y coordinate is 10, it's that location. But do we know the time coordinate of this point? Yes or no? We don't know that yet. We don't know that. No, yeah, you're right. So Michael says no, which is correct. We don't know that yet because we need to figure this out. So slope is 13.04. But we know this point. So we can write the equation of the line. So what I want you to do is I want you to give me the equation of this line right here. It has a slope of 13.4. And then 1 point on the line is 23 and 5. So use the point and slope and give me the equation in the form of x and t. Let's take a couple of minutes to write down the equation in the form of x and t. So x equal to 13.04 over 60. And I should probably say the slope actually is not 13.04. It's 13.04 over 60, right? Because our time axis is in minutes. So 13.04 over 60 is the slope. 23.5 is the time. So you can just plug that in. If you have the equation, could you let me know, please? So I see an equation here, which I'm not sure, is that quite correct? Because is everybody got the equation that Lauren got? $13.04 times X could be correct, actually. But yeah, the origin could be, yeah, that's right. So it's actually, yeah, okay, perfect. So yeah, so if you divide by 60, I think what you'll get is 13.04. Yeah, it's kind of weird that in this example, we got a pretty interesting equation of this line right here. Because if you look at this, I mean, obviously this diagram is not drawn to scale, but so the way this equation shakes out is that it has that different slope, and if you extend that slope, and this diagram is not to scale, but it turns out that this is a line that passes through the origin. So the equation of this line would be 13.04 by 60 times X. So that would be the equation. Now, if you want to find where does that meet, what time does this line get to X equal to 10? That should be easy to get as well, right? 13.04 over 60 times T. So 600 divided by 13.04. So you can figure that out too. So if you want to figure out at what time does this line meet the x-axis, 13.04 okay, does anybody have the time? So now if you want to figure out, because your key thing is this figuring out this point now. Yeah, that's right. 46 is what I got as well. So that means this Q will dissipate at T equal to 46. So if you kind of try to find this point, because the line equation is fairly simple. So the equation of the line that we got, the last line. So if you want to write down the equation of this line. I don't know why. So has everybody got time equal to 46 for this equation? So we got the max Q and everything. We figured out all of that thing. Now the Q dissipates when the recovery shock waves which has an equation of X equal to 13.04 divided by 60 times T times T, right? It has this equation, right? Reaches X equal to 10 kilometers, right? Because obviously once it reaches 10 kilometers and your new demand is only 2,600, because remember, the demand that goes with that recovery shock wave is only 2,600. And when that demand reaches all the way up to X equal to 10 kilometer, where the capacity is 3,200, then there is no Q, right? The Q goes away. So if you solve for that, so plug in X equal to 10 and solve for time. So you get T equal to 46 minutes. Any questions about this? Somebody got a different answer or any of these stuff? So the Q was a 360 vehicle Q impacted by the Q at its worst. And then the recovery begins at that point at t equal to 23. And in 23 minutes, so the queue forms for about 17 minutes and it goes away in about 23 minutes because the recovery shock wave is a little bit slower than the forming shock wave in this example, which is fine because the forming shock wave was moving at 17.65 kilometers per hour backwards. The recovery shock wave is only moving at 13.04 kilometers per hour forwards. So it took a little bit longer to dissipate the Q than it did to form the Q, which is fine. I mean, it could play out either way. It depends on the flow rates and densities and whatnot. But okay, questions? Any of these points not clear, please? Now, at this point, I know a lot of you had questions about shockwave speeds and how do we find the max Q, and then obviously how to solve this problem as well. Any questions that remain unanswered about shockwave and recovery and whatnot? Please let me know. Anybody did the input-output of this problem? Anybody did the input-output portion, input-output method for this problem? Okay, good. Thank you, Dana. If you did input-output for this problem, did you get the Q dissipating at 46 minutes also? If you did the input-output method for this problem, did you get the Q dissipation time to be t equal to 46? Maybe we can quickly go over the input-output method as well. And that's our verification that, the input-output method, when we solve it, you will see that your max Q length would actually come out a little bit lower. Okay, but your Q dissipation time will come out the exact same. And that's the formulation that the two methods use. That's different. They define the Q in a different way. The shockwave defines it more accurately in that the Q actually takes the roadway space, but the input-output modeling basically just assumes a vertical stack Q that everybody only queues up when they get to that point of X3. You don't account for any of the slowdown or anything like that when you're looking at queues in the input-output method. Okay, so let's do the input-output example unless there are any questions about the shockwave here in this problem. So input-output method is actually a simpler problem because all you need to do is you need to figure out the arrival equation and the departure equation. So I'm going to just write arrival rate. So if you look at the arrival rate, initially the arrival rate is only once the queue starts, right? Like, so we are going to write the arrival rate is 3,800 vehicles per minute, or 3,800 over 60 vehicles per minute. And then the arrival rate reduces to 2,600 over 60 vehicles per minute, right? And similarly, we can write the departure rate. What is the departure rate? Departure rate is something even simpler because it never changes really. It's only always going to be 3,200 vehicles per minute, or 3,200 over 60 vehicles per minute. Now, all we need to do is write down the number of arrivals and number of departures, right? Number of arrivals and numbers of departures, and then these rate changes happen. So this happens between 6 to 20, 60, 26. And then this happens to be at t greater than 26. Okay, so because we offset everything by 6 minutes, because that's when everything will arrive at t. And then the departure rate is all for all values of t My departure rate is exactly the same. I got the warning that my internet connection was unstable, so I hope you didn't miss anything. If you did, please let me know. If there are any questions, how I wrote down these arrival and departure rates. Okay, so now, once we write the rates, then we just have to write the number of arrivals. So we write number of arrivals, pretty simple. 3,800 over 60 times T. So I'm going to just multiply that by T. But I'm not going to multiply by T because, I want to offset everything by T, T equal to 6. So I'm just going to multiply by T minus 6 because my Q begins at T equal to 6. So I'm just going to measure that. But then at T equal to 26, at T equal to 20, at T greater than 26, once the T equal to 26 is passed, I would have certain number of vehicles that would have arrived by then. But then my arrival rate would be T minus 26 times 2,600 over 60. Okay, does that make sense to everybody? Is this correct? When I'm trying to write the number of arrivals, is this equation correct? Is there anything wrong with this equation here? What is wrong with this equation right here?
Oh, you have to do 6 times 3,800 divided by 60 added into the bottom equation.
Yeah, so basically what I'm missing here is that because my goal is to write the total number of arrivals, the piece that I'm missing is that I have not yet accounted for the vehicles that arrive within that 20-minute period. I have not added those yet. So I do need to add those. So in 20 minutes, between T equal to 6 to 26, that many vehicles would have arrived. So I need to add 20 times 3,800 over 60. So I need to add a 20-minute period when 3,800 vehicles would have arrived. I need to add that piece to this. 20 times 3,800 over 60. Because for 20 minutes, the vehicles were arriving at that rate. So let me look at what's on the chat here. Yeah, so it's 1,266.67, which is fine. And again, I try to keep them in decimal for now, because once you introduce rounding errors, they keep compounding a little bit throughout the problem. So I'll just keep them in fraction for now, but your number is correct probably, yeah. Okay, now number of departure, fairly simple. Number of departure is easy because the departure curve does not actually change. Number of departures is fairly simple. Number of departure would be always 3,200 over 60. And I multiply that by T minus 6 times 32. Okay. And all I need to do to figure out when does my Q go away. Okay. First of all, the Q length expression then is just, if I want to ever write Q length, figure out any Q length, I just need to do number of arrivals. How many people have arrived minus number of departures, right? Number of arrivals minus number of departures. And obviously that there will be sort of a discontinuous function at T equal to 26, which is fine. We can account for that. So number of arrival, again, you have to apply that little marker here. And for T greater than 26, this will be the equation. Right? questions about this? Okay, so we can write the Q length expression this way if we are clear on the two expressions that we've written. And then when does the Q go away? When number of arrivals minus number of departure becomes 0, or the number of arrivals are equal to number of departures. And then all you need to do is just take this number, and I'm going to highlight right now, and subtract from this number and solve for t, and set that equal to 0 or solve for t. So, and we can check because we have the answer from the shockwave method. You can check if t equal to 46 sort of fits into that. So I'm going to just quickly check if t equal to 46 fits into that. And you all can also verify and see if that gives you, when these two expressions that I've highlighted become equal, means number of arrivals become equal to number of departures. That's when my Q length goes to 0. And that would mean it's 3,800 plus 2,600, 6,400. Yeah, that's right. So if I plug in t equal to 46, I just verified that, yes, number of arrivals become equal to number of departure. So if you solve for this, when does the Q dissipates? When the Q goes away, it's when this number of arrivals, becomes equal to this number. Okay, and if you solve this, you will get t equal to 46. So same answer. Now, if I want to find out max Q length, okay, I want to give you the opportunity to now solve for the max Q length, please. So let's now take a minute. We have the Q length expression. I want you to find out what is the maximum number of queues or maximum number of vehicles in queue according to the input-output method. So your job next is to figure out max queue lengths. Length rather, max queue length. So what you need to do is like the maximum value of this expression. So your job is to find the maximum value of this expression and highlighted in green right now. So number of arrivals minus number of departures and that would be maximum when? At t equal to? What time would that be maximum? That's right. Simon says it's t equal to 26. I agree with him because that's the time when the flow rate actually reduces. And by that point, it's only when the flow reduces does the Q length start to dissipate a little bit. So before that, Q just keeps growing and growing and growing. So it keeps growing until t equal to 26. So if you plug in into arrivals, this is arrivals, this is departures. So maybe I should so this is arrival expression. This is the arrival, sorry, bad choice of color. So this is your arrival equation minus the departure equation. You just plug in t equal to 26 and you will get what? Let's see. What did you get? The Okay, does anybody have the number for me? $200. Simon says 200. Did everybody get 200? Yeah, same. Good. So okay, max Q is only 200 vehicles according to the input-output method. Okay. So that's the correct answer, of course. And the idea is that input-output method, because it assumes that the roadway doesn't take, the queue doesn't take space on the roadway, and everybody just magically gets to X3, wherever the bottleneck is, and just stacks up vertically. That's sort of the abstraction of the queue that the input-output method uses. And because of that, they find that there is only 200 vehicle long queue at the bottleneck. So, but that's not quite correct. But we also know that it doesn't matter when you're trying to calculate when would the queue dissipates or even the total delay and whatnot. So it doesn't matter what those calculations are going to be. So that's the difference. The max queue, that the input-output method tends to undercount the queue because of how it formulates that idea of the queue. But the queue length or the vehicles that are impacted by the queue is more accurately represented by shock wave. And that's why we get the exact expression of how many vehicles will be lumped up in that slowdown. It will be 360 vehicles, or what we got from the shock wave approach. Okay. So are there any questions now? Okay, did we cover up? I think, to my knowledge, we have covered all the questions that were there in the muddiest point surveys. Shockwave speed, the difference between how to calculate shockwave speed, how do you find the point when there is no chart given? Or are there any other questions that we haven't yet addressed that you would like to ask? And I think this I've already shared with you. So if you want to see this document also is already shared with you. So you should be able to see that. So I'm just trying to go back to the, yes, okay, let's see what the question is. Yeah, the exam. So the question that I got via chat was that, where do you start? So we'll start with that lane change model. And then we'll cover, lane change, shock wave, all of that stuff. Yes. So yeah, there may not always be a diagram to look at, but the diagram itself is, you can create a very rough diagram very quickly. So the problem itself would not be so complicated that you cannot create the diagram. I will not have you look at two different shock waves in the same problem. It's a 50-minute test, and I'm very well aware of that. And I need to test the whole gamut, as Peyton asked, like, from lane change all the way to shock wave and to fluid and surrogate. So yeah, no, there would not be a test in which you will be looking at multiple shock waves. There's going to be one shock wave. And for that one shock wave, you should be able to figure out what's going on. And one thing I want to sort of look at in this problem too the Q forms when the demand exceeds capacity, right? The Q forms only because there's a total demand of 3,800, 3,600 from here, 200 from the ramp. And that reaches the point where the bottleneck capacity is only 3,200. Now, if the bottleneck capacity, let's just say, if somehow this bottleneck capacity were to be lower value, to higher value, or somehow this demand value was lower, no Qs might also form, right? So anytime the Qs only form, or the shock wave will only form when the demand exceeds capacity. If the demand does not exceed capacity, there will be no Q forming. Okay, so be very careful with those numbers, because, and then you will also see that, like, if you try to do something like that, you'll start seeing that there is actually no congestion at all. So you'll see some weird answers with regards to shock wave. So always be careful to go back to the fundamental principle. For example, in here, the bottleneck capacity was 3,200. The demand is 3,600 plus the 200 from the ramp, got you to the point where it was 3,800 vehicles per hour demand, right? But if the demand did not exceed capacity, there will be no Q. So then your answer will be no Qs will form, and you don't have to worry about any of this stuff. So I will always kind of look at the problem carefully. What is asking? What is thinking about it? So just always take a couple of minutes to review the problem carefully before you start jumping into the calculations. Any other questions?
Yeah, I have a question.
Yes, please, Michael.
Are we expected to know how to draw the diagrams?
Not to scale, definitely. But I would expect you to be able to do what I did here, for example. Not to scale, definitely. But thinking about these kind of situations, this kind of a diagram like that, I think it might be helpful when you're trying to solve the problem.
Right. Okay.
So yeah, I think to some extent, I want you to be able to think about the time space diagram or the input output Q diagram that we sometimes do. Although input output Q diagram is not necessarily always required, because remember, when we solve the problem, we never have to actually get into the diagram. I can write on the expressions, and that works fine. But I think for shockwave, probably it will be helpful for you to kind of think about, what the shockwave might look like and so forth. So
okay.
So maybe not to scale or anything like that, but just for your own clarity, at least for shockwave, I feel much clearer when I'm actually drawing the diagram and drawing out different regimes and figure out which regimes are the two shockwaves separating, stuff like that. So that helps me a little bit when I have a diagram that I could draw.
Okay. Thank you.
Yeah. So no class on Tuesday. I will have some material for you to review. So the question was asked, is there no class on Tuesday? Yes, the plan is still to have no class. However, there's one little wrinkle to that. The wrinkle is that, because I still, as I told you, still haven't tested negative. So it's possible that I might not be able to make the trip, right? So I'm feeling much better than, for example, Saturday, Sunday, Monday morning, I was feeling terrible. But, by the time Tuesday rolled around, I was feeling better. And today I'm feeling even a little bit more better. My problem right now is that I'm still testing positive. I still have a little bit of remnants of sore throat. So the long story short, if I still test positive, let's say on Sunday, then it's possible that I don't travel. In that case, we could have sort of an open class session where I can answer any questions or anything like that. But as of now, right, and I'll email you about that. If I don't travel, then I'll let you know about that. But if that is the case, then we can have an open sort of class, because I fully expect to be able to recover by Tuesday. And I will still have some, some time for you to meet up with me. I'm still finalizing my conference schedule, and I'm still looking at whether I'm even able to travel or not. So I'm going to give you some times when I'll be available for you for me to answer your questions via Zoom for sure. But if I'm still in town, we can even make it in person if I don't end up traveling because of not testing positive or not testing negative rather. So yeah, sorry about this all weirdness, but this is how we live now. So yeah, so that's the plan anyway. Okay, so I don't have a lot of practice exam questions. So your practice exam questions are basically your homework problems and what I asked you for practice problem for the shockwave and queuing theory, and then the lane change problem. The problems are going to be very, very similar to what you've just seen. So I don't have a lot of practice problems. This is a graduate class, so I'm not relying on material that is sort of well defined, where tens of authors have written textbooks about. So I don't have a lot of sort of materials to pick from. But if you sort of review the lecture notes, review the slides that we had, and all the homework problems, basically the test will be very, very similar to those. You just have to read it carefully, manage your time, and that's it. So I don't have any more practice problems for you to work on. You can try to play around with some of these numbers, shockwave numbers and so forth. And if you have any doubt or something, you can always ask me. I think the best bet would be to maybe give it another day or so, and then try to solve the problem from scratch again, and see where you get hung up. So that will be my advice for you to practice, but no real practice problems. No more real practice problems, I'm afraid. Now, if you're wondering if I could ask you some questions from the lab and stuff, yeah, I mean, there might be some questions from the lab. Obviously, I'm not going to ask you like step by step how to do this in vSim, but I might ask you, might ask you like, when you're trying to define the priority area, what are some of the things that you look for when you're trying to validate a vSim model or calibrate a vSim model appropriately. So you look for like ramp merging and stuff like that. And yeah, so there will be like, there might be some simple questions around vSim calibration and validation. I might ask you to define like, okay, what is the GEH statistic, for example? What is the role of GEH statistic in vSim validation, stuff like that. So I fully expect you to know that. So there might be some sort of questions from the lab sessions. But again, I won't ask you like, how to do this in vSim, which button to press and things like that, but sort of more big picture type questions. Okay, when you're trying to validate, what would the GEH statistic look like? And, I can even, but I'm not going to ask you to remember the GEH statistic formula. You can write down in your notes. And I'm just going to give you the GEH statistic formula. I'm not asking you to remember the formula, but you should know the role of this GEH statistic. Like, how do you apply it? What is the purpose of it? How do you validate a network with it or things like that? But not step by step in vSim or anything. That makes sense. Other questions? Okay, if there are no other questions, I'm going to stop now. And I have a couple of things for you that I'm going to maybe stop the recording for now. Oh, and then one more thing, please be sure to review the material from the guest lecture. So there is a recording for that I've made available on Canvas. So please be sure to watch that recording if you could not make the lab that day. But if you were, that's great. So just kind of review I don't have the PowerPoint slides because they haven't made it available, which is fine. But just kind of quickly watch that video. Just kind of look at, there might be some true false type questions from that video, from the guest lecture. So please go ahead and watch that.